Given a set of data as to how the amount of the reactant, say, chemical species A, changes as the reaction proceeds, it would be good to predict the amount of A at any given time, beyond what is gathered for the experiment, for example. This is where the integrated rate equations come in handy. For instance, for a zero-order reaction, the integrated rate equation is of this form. The form of the equation is different for a first-order reaction, which is of this form. The objective of plotting the experimental data, then, is to determine what the reaction order is. Once we know the reaction order, we can determine what form the integrated rate equation takes, as well as the value of the reaction rate constant K. To test whether a reaction is zero-order, we can plot the concentration of A versus time. If we obtain a straight line graph, we have determined that this reaction is zero-order with respect to A. The value of K is the equal to the negative of the slope of the trend line. If the plot of the concentration of A versus time is not linear, we can take the natural logarithm of the concentration of A, then plot this versus time. If this plot is still not linear, we can take the reciprocal of the concentration of A, then plot this versus time. To refresh your memory on how to do this, consider the following reaction. This is an example of a dimerization reaction, commonly done in the manufacture of pharmaceutical drugs. In a dimerization reaction, two molecules of the reactant, called the monomer, come together to form the product, which is called the dimer. Shown below is the concentration of the monomer as the reaction progresses. From an initial concentration of 0.0054 mol per liter, the concentration decreases as the monomer is used up. For this sample problem, we are to determine the average rate of the reaction from 10 minutes to 70 minutes, what the concentration of the monomer is after 3 hours, and what the half-life of this reaction is. Given the tabulated data and the balanced chemical equation, the rate of reaction can be expressed in terms of the rate of disappearance of the monomer. Through appropriate substitution, we find that the average rate of the reaction between 10 and 70 minutes is 2.0 times 10 to the negative 5 molar per minute. In Microsoft Excel, or any similar spreadsheet software, we type in the experimental data. We select the data, then generate the graph by clicking the Insert tab. This button over here allows us to generate a scatter plot for the concentration of the monomer versus time. Using Quick Layout, we can properly format the plot so that the chart title and the axis titles are shown. To edit these, we simply double-click the necessary fields, then type in the labels. As you can see, the graph is not linear. Therefore the reaction is not zero-order with respect to the monomer, and so we next test if it is first-order. To do this, we get the natural logarithm of the concentration of the monomer at each given point in time. We can do this individually for each value of concentration. Alternatively, we can set the mouse cursor above the green square at the bottom right of the cell, click and hold, then drag to copy the formula for the remaining cells. Once this is done, we select the data for time and the values of the natural logarithm, then generate a new plot, to test if the reaction is first order with respect to the monomer. The graph still has a slight curve to it, which tells us that the reaction is not first order. We then get the reciprocal of the concentrations, then plot this with respect to time. This is the graph we generate. We see that the graph is now more or less straight. The next thing we do then is to generate the trend line. To do this, we select any of the points on the graph, right-click it, then select Add Trend Line. On the toolbar to the right, we select Linear, then click on Display Equation on Chart, as well as Display R² value on chart. The equation of the trend line gives us the slope, and therefore the value of the rate constant. The R² value shows us how close to being a straight line the scatter plot is. The closer the R² value is to 1, the straighter the scatter plot is. You can generate the trend line for each graph and compare the R² values if you are not sure if the scatter plot is already straight. From the graphs we made, we can then conclude the following: the reaction is second order with respect to the monomer, the value of the rate constant is equal to the slope of the trend line, and the integrated rate law equation is as follows. Now that we know the integrated rate law equation, we can now compute for the concentration of the monomer after 3 hours. First we convert the unit so that it is the same as that in the tabulated data we used to find the equation, then we simply substitute the value. After one half-life has passed, we recall that the amount of the reactant is reduced by half. Knowing this, we can then use the integrated rate law equation to compute the half-life. Note the discrepancy between the calculated value and the experimental data. This is because the scatter plot is not perfectly straight, so there may be some difference from the experimental data. Either value is acceptable. To help you practice what you've learned in this video, please try answering the following problem taken from your long quiz. The answers are provided to help you check whether you got the correct answer or not. For further studying, you are advised to go over the following examples taken from the textbook.